Welcome back for the 7th week of this lecture series on the NPTEL course on principles of polymer synthesis. Over the last week or so, we have been talking about principles of chemical reactor design, and if you remember, towards the end of the last week we discussed about CSTR, steady state multiplicity, and we also tried to solve some problems. So, today is the last class as far as the chemical reactor concept is concerned. After that, we will go into the synthesis of commercially important step growth polymers. So, let us do maybe a couple of more problems before we finish this topic on the design of chemical reactors. So, if you remember, last week we finished with this particular problem here. So, we took some reaction, say A plus B goes to C, and the rate equation is also given. For simplicity, it is first order in A and 0th order in B, and the rate constant was given as a function of temperature, and also some other information were given like the heat capacity of the respective reacting species. It was also assumed that the heat capacity is constant with temperature, does not change. The temperature of the heat transfer fluid, temperature of the inlet, volumetric flow rate in, and molar flow rate in, all these things were given, and delta H of reaction, that is the enthalpy of reaction, was given minus. So, it is exothermic reaction. Also the heat transfer characteristics were given. If you remember, U is basically the heat transfer coefficient of the material of construction of the reactor, and A is basically the area over which the heat transfer occurs. CSTR volume was also given. So, the question was find the steady state operating conditions, and we used this energy balance equation in the steady state for CSTR to find out x, that is the conversion as a function of temperature directly. So, this was linear, and then what we also do is separately we apply mole balance to the expression of conversion, and what we find is the variation of x as a function of temperature, and there it is not linear because the small k, the rate constant, contains the temperature in the exponential form e to the power minus activation energy divided by R into T, and then the intersection of these two graphs will give you the solutions. In this case, there are 3 intersections. So, there were basically 3 solutions. So, what I will do today is to do the same problem again, but for a polymerization reaction, an exothermic polymerization reaction, specifically the polymerization of styrene, and we are going to have some assumptions that are going to simplify our problem. You have to remember that in reality the problem will be little bit more complex, but just to give you a correlation with the concepts that we have shown here, I would like to solve that problem with those nevertheless with those simplified assumptions put in place. So, let us have the definition of the problem then. So, the problem is something like this. Let us say we have a CSTR, continuous star tank reactor, which has a volume of 20 meter cube, and you are polymerizing styrene in this reactor, and what is given is the following: the molar flow rate in is given, is that is 91 moles per hour, and also the volumetric flow rate is given, which is 20.4 meter cube per hour. Now, these things I have optimized for to demonstrate the concept that I have already shown in the previous problem. Now, these things of course, you can also control. This is user controlled, and the heat transfer characteristics is like this: U A, U into A. U is the heat transfer coefficient, A is the area over which the heat transfer occurs, that is equal to 1 into 10 to the power 4 joules per hour Kelvin. Now, some of the data I have taken from literature, like the heat capacity of styrene. Heat capacity of styrene is equal to 180 joules per Kelvin per mole. T0 this again I am defining. See, T0 is the inlet temperature, let us say that is 295 Kelvin, and Tc is the temperature of the heat transfer fluid, which is 305 Kelvin. And again from the literature, for the styrene polymerization, the Kp is something like this. This is the rate constant for propagation. This Kp, the value is 1.051 into 10 to the power 7 e to the power minus 3557 divided by T. Okay. And Kt, which is the termination rate constant, which will be orders of magnitude higher than the propagation rate constant. If you remember our discussion on the principle of radical polymerization, we had mentioned that, and indeed this is so. 1.255, in this case it is 2 orders of magnitude higher, 10 to the power 9 e to the power minus 844 divided by T. And Kd, that is the dissociation constant for the initiator. We are assuming that in this case we are using benzoyl peroxide as initiator. Now, Kd is very small, it also has a dependence on temperature, but for simplicity again I am just assuming it is constant at 10 to the power minus 5. Now, small f, which is the initiator efficiency, let us assume it is 0.6, and let us say the initiator concentration is 0.05 molar. Now, remember, in actuality the situation will be little bit more complex, because your efficiency of the initiator also can change with the progress of polymerization. Not only that, the initiator concentration can also drop with the progress of polymerization, and this Kp and Kt, if you remember the concept of auto acceleration, what can happen is that with the progress of polymerization, your Kp will decrease, your Kt will decrease, but Kt will decrease much more, so that the rate of polymerization may increase significantly. Those things we are not taking into account. We could, things will become more complicated, it has to be, the situation has to be approached differently. Those things we will not discuss. Just to have a parallel connection with the previous problem, I brought in this polymerization situation into the scheme of things, and assuming some of these simplified things, and these Kp and Kt, these are literature values. The initial stages of conversion, they will be having this kind of dependence. Okay, so with these simplified assumptions we will progress. So, the question then is, find the steady state operating conditions. So, what are the steady state operating conditions? So, this is the question. So, we will do the same that we had done for the previous example. So, we will go to the energy balance, and from the energy balance we will get the conversion as a function of temperature, the linear function, and then what we will do separately, we will apply a mole balance to the conversion, and we will get the dependence on temperature, which will be non-linear, and then the intersection of these two graphs will give you the solution. If it is one intersection, then there is only one steady state available under this situation. If there are two, then there are two steady states available, and typically you will not get more than 3 intersections. So, the maximum number of solutions that you can get are 3. So, steady state operating conditions, and if you remember in the previous example we had 3 steady state operating conditions. We obtained 3 steady state operating conditions as the solution of the problem, and if you remember, we had shown, if you look at the graph in the slide, in the PowerPoint slide, we had shown this thing in the graph, that the energy balance and mole balance equation. So, the energy balance and the mole balance. So, these two, energy balance is basically the conversion as a function of temperature that we obtained from the energy balance equation. So, that is what we are plotting against the reactor temperature, and the red curve is basically again conversion as a function of temperature, but we are using the mole balance equation, that is why it is non-linear. The exponential term is there, and basically you had 3 intersections there, so which gave you 3 solutions. So, each intersection corresponds to a particular reactor temperature and a particular conversion. So, if you are working at that particular point, the steady state, you are fixing the reactor temperature and you are getting a specific conversion, and as you know, under the working conditions in steady state, the conversion of the CSTR, it does not change, it remains same. So, this is what we had solved before. So, now this is the problem that we are going to solve. So, again for the energy balance, this is steady state energy balance. So, 0 equals to minus Cp of styrene into T minus T0 plus delta H reaction into minus X plus UA divided by Fa0. This is the equation, if you remember. If you do not, you can just go back and recapitulate. This is the original equation. So, whatever number of reactants are there, you just add the heat capacities, and we are assuming that the molar flow rate is the same for all the reactants. In this case, we have only one reactant though. So, you put all these values there, and then you divide by your molar flow rate, and so that will be coming here. So, that will be UA into Tc minus T divided by Fa0. Exactly, that is what we are putting here. So, this is basically Tc minus T. Okay. So, if you put the values in there, so it will be 0 equals to minus 180 into T minus T0 is 295 minus, okay, one more value has to be given for you, which is delta H reaction. It is exothermic reaction, styrene polymerization. Vinyl monomers, when they polymerize, they will typically polymerize exothermically, a lot of heat will be generated. So, delta H reaction here, this is again from the literature that I had obtained, is minus 63,000 joule per Kelvin, joule per Kelvin per mole. In fact, it is not joule per Kelvin, it is joule per mole, excuse me. So, this is delta H reaction minus 63,000 joules per mole, and okay, the value of UA is also given. So, we can proceed. So, this is 63,000 into minus X plus, you just put the values of UA and Fa0 and mind the units. The Tc is also known. So, if you put all these things, then you will get something like this, 109.9 into 305 minus T. So, from here, I mean, according to what I have calculated, I have already worked out the problem. I do not want to sit and calculate here. So, it is minus 1.375, and of course, you can figure it out yourself how the calculations are proceeding after when you look at it with some time in hand. So, this is, so as a function of temperature, then you have the energy balance equation. So, this will give you a linear plot, which is basically equivalent to your RT versus T plot. So, this you can plot. Now, the second thing is little bit more involved. If you are going for the mole balance equation, remember that accumulation is equals to molar flow rate in minus molar flow rate out plus RA into V. Now, from this equation, if you remember what we had taught before, the rate of polymerization is basically equals to, I mean, in this case I am putting RA or R, let us say A is the styrene, whatever. So, rate of polymerization is your rate constant, basically it will be negative, because this is rate of disappearance of the monomer, into the monomer concentration into small f into Kd into I divided by Kt to the power half. This is something that we had derived before, just right at the start of the discussion of the radical polymerizations. And so, this is the expression that you can use then in this equation. So, if you use this expression, then what do we get? So, just replace the R here with this expression, and then also remember that your Fa is basically V0 into concentration of A. So, molar flow rate out, in this case this is molar flow rate out, is equals to volumetric flow rate into concentration of A, which is the, this is concentration of A or the concentration of styrene in the reaction mixture, which is constant because it is operating in steady state. Now, V0 is basically the molar flow rate, is the volumetric flow rate in, that is why the 0 is there. So, inlet volumetric flow rate. Now, this is also equal to the outlet volumetric flow rate, because both are equal in the case of liquid state reactions under steady state conditions. That is why I am putting V0 here, even though this is the molar flow rate out. So, just put those values in here. So, if you put that value here okay, all right. Let me not skip the step. Let us go back to this, because if you skip steps, you may commit always mistakes, it is possible. not always possible to find the mistake at the moment you are doing the math. So, Fa0 minus V into Ca, so that is minus V into Ca or V0 into Ca minus Kp into Ca into F Kdi divided by Kt to the power half into V, and also remember that V by V0 is basically your residence time. So, if you take that into account, and then you can get an expression of Ca from here, and if you remember again that Fa is basically V0 into Ca, then you can replace the expression of Ca from here, and the final expression that you will get is something like this: Fa0 divided by 1 plus Kp into Fkti divided by Kt to the power half into tau. I mean, I just summarize this for you, you can figure it out yourself. So, this is tau because V0 into Ca, so basically Ca is Fa0 divided by this V0 plus this into capital V. Now, when you are multiplying by V0, your V0 is coming here, that V0 if you take down, so V0 by V0 it becomes 1, and this is capital V by small V0, it becomes tau. So, this is your expression. Now, if you remember that your conversion in terms of the molar flow rate in and molar flow rate out is basically equal to Fa0 minus Fa divided by Fa0, and then if you replace the expression of Fa from here, then finally what you will get is x equals to 1 minus 1 divided by 1 plus Kp into Fkti divided by Kt to the power half into tau. So, this gives you the dependence of x on temperature from your mole balance equation, and remember here that this tau is basically known for you because you already know the volumetric flow rate in and you already know the volume of the CST. So, this divided by this is your tau, and okay, let us see. So, if you look at the expression here, also look at the units, it is a per, so basically this is if I remember correctly, this is per second. So, if you have the unit here per second, when you are bringing those expressions here, ultimately there will be a per second term remaining. So, basically you have to multiply by 3600 because you have to go to per hour, and that is also because the tau is in terms of hour, because this is 20 meter cube divided by 20.4 meter cube per hour. So, those things you have to keep in mind, otherwise you will not get the correct result, and you know the value of I, Kd, etc., all these things you know. So, you basically can have an expression of x in terms of t, and although I will not show you the graph that I have plotted, unlike the previous problem where I had shown you the graph, but I will just write down the result for you. So, this is the result. Basically it has 3 solutions. So, you have 3 steady state conditions, operating conditions that you can choose from. So, 334, 376 and 440 Kelvin, these are the 3 temperatures, and at these 3 temperatures if you are operating, the corresponding conversions are 0.16, 16%, 0.36, 36%, 0.65, 65%. So, you have these 3 steady state operating conditions that you can choose from at that particular inlet temperature and at all those fixed temperatures that we have. So, inlet temperature is fixed, your heat transfer fluid temperature is fixed, your UA, which is your heat transfer coefficient multiplied by the area of heat transfer, those things are fixed, and then you can have this solution. And something you have to remember, of course, this is a simplified thing because you know we did not take into account rotor acceleration and what not, but something you need to keep in mind that oftentimes your the lowest temperature that you can operate in, the conversion may be very small, so small that your molecular weight that you are going to get at the end is not industrially very important. So, you may need to operate in the middle steady state or at the higher steady state. Now, remember that this is the unstable steady state in these kind of situations, these two are stable steady states. Now, typically in this middle steady state if you are operating, you will get say 25% to 30% of the yield per reaction pass. So, if you are looking at that, that will be good enough as far as the industrial grade polymer is concerned for this kind of situation, say radical polymerizations if you are doing, say styrene polymerization if you are doing. So, you could also tell that I would go to very high temperature and then I can get very high conversion. So, one problem there is that oftentimes this temperature that you have may be quite close to your ceiling temperature. So, that is a problem to do the reaction in, and also you are doing the reaction at a high temperature, and remember that it is an exothermic reaction. So, the safety is also an issue. So, these things you need to keep in mind, and also something that I showed before, if you increase the temperature of your reaction, what can happen is that your degree of polymerization and hence the molecular weight of the polymer might decrease. I mean, I am talking about thermally initiated radical polymerization. So, those are the things that you need to consider when you are thinking about which steady state to use. Now, something else that I wanted to also mention here is that you have, so this is the problem that I have already solved. So, that is the end of it. So, let us go back and discuss something here as far as the energy balance equation is concerned under steady state, something that you need to keep in mind. Now, your CSTR may be operated in isothermal condition, or it could be operated in an adiabatic condition, or it could be operated in a non-isothermal condition. You need to be able to differentiate between the three. So, if you go back to the equations in the script, it is easier to understand why. So, you have this expression here. Now, in the simplest of terms, let me see if I can locate in the previous week what I had derived for you. So, as far as the energy balance expression was concerned. So, this is, here is one expression that I have got for you. Say for example, you have this expression, I mean this q dot is basically this. Okay. So, q dot is basically this term. Now, I mean if you have to directly plot say R t versus t, remember that when you are plotting your x versus t that you have got from the energy balance equation, that gives you an equivalent of R t versus t. But if you are asked to plot the rate of heat taken away as a function of reactor temperature, that is the R t versus t, or you are asked to plot G t versus t, that is the rate of heat generated as a function of temperature, you can directly go to this particular equation, the steady state. So, if you look at this particular equation, so this part, this part basically will give you the the rate of heat generated. So, if you look at this particular term, it is basically the same as this particular expression in different forms they are. So, if you look at this particular expression here, so this part will give you the rate of heat generated as a function of temperature, because the temperature term will come here, because this you can express in terms of x if you remember. So, that will be minus of x when you divide by Fa0. Okay. So, that is the term then you can directly take, because that will give you the Gt as a function of t, and then you can plot against t. Now, if you take this term on this side, then collectively this term minus q dot, that term will give you the R t versus t plot. Now, of course, you divide by Fa0 that side also. So, it will be Cpa into t minus T0 minus q dot divided by Fa0. You take this term on this side and you divide whole through by Fa0. So, that term, so this minus this will then give you the R t versus t curve. Now, if you are looking at your expression, then I mean this expression is basically the same as this expression. So, if you are working under isothermal condition, something that you need to keep in mind, if you are working under isothermal condition, then what will happen is that your inlet temperature will be equal to the temperature in the reaction mixture. So, basically then this term will go. So, you are only left with these two terms in this case. So, if you are working in isothermal steady state situation, then this term will go, T equals to T0. And if you are working in adiabatic situation is a situation where there is no heat exchange with the surroundings. So, then this heat transfer term will go. So, those things you need to keep in mind. So, the situation that we are working in, although we are keeping the temperature of the reaction mixture constant, strictly speaking it is something different from your typical isothermal situation that we talked about, because its T is not equals to T 0. So, basically you are operating in a non-isothermal condition, because remember that if it were isothermal situation, your temperature of the reaction mixture will not rise in the first place as far as its value with respect to the inlet temperature is concerned. So, you have allowed the temperature to rise to a certain extent, the difference being T minus T 0, T being the reactor temperature and T 0 being the temperature at the inlet. Now, and then you are maintaining this difference in temperature by taking away the heat from the reaction mixture by using a heat transfer fluid. That is the idea. So, you are operating in a situation where your temperature of the reaction mixture is higher than the temperature of the inlet, so this particular situation is not your adiabatic situation, because you are taking away heat. So, when you are operating in an adiabatic condition, in a steady state condition, basically you are not having any heat exchange. So, the heat transfer term will become 0. So, if you are asked a problem where you are told that the CSTR is operating in isothermal condition, then that particular term where T minus T 0 is there, that term goes to 0, because T equals T 0. If you are asked about a problem to find about about the information on the steady states in adiabatic situation, then the heat transfer away the term U A into this T minus T C minus T, that term becomes 0. So, those things you need to keep in mind. So, okay, so that is it overall. That is what I wanted to discuss as far as this particular thing regarding the reactors are concerned. Now, in a nutshell, let us try to summarize certain things. So, if you remember from the start, what we had done is basically the same. So, we are now trying to summarize what we have learnt about the chemical reactors. So, basically we talked about flow reactors, we talked about batch reactor. So, among the flow reactors we talked about different kinds of flow reactors like plugged flow reactor, like CSTR, which is continuously stirred tank reactor, and also we talked about batch reactor, which is different, which is not a flow reactor. And remember that other than plugged flow reactor, we also talked about packed bed reactor, which is also a kind of flow reactor, and they have different design equations, and these things we discussed. And the design equations initially we derived from simple consideration of mole balance in steady state condition, and afterwards what we also argued is that we need to express these design equations in terms of the actual conversions that you are targeting for a particular chemical reaction to be conducted in that reactor. So that ultimately the design equation will contain the expression, in this expression the conversion, and then for a targeted conversion in a particular steady state, you can know, for example, how long you have to keep it in the batch reactor, because you are not taking out anything as long as the reaction is going on. We have done this kind of problem also during the progress of this course. And if you are in a flow reactor, for example, in a CSTR, then you have to know the volume, because the volume controls the conversion and not the time, because the time is fixed that way, and it is a steady state situation. And of course, there is a term which is the residence time. If you can increase the residence time, which means your reactants are there for more time in the CSTR, that means there is more conversion correspondingly, so on and so forth. So, those things you need to keep in mind. These are intricate, some of the intricate details, but things are simple in general. So, we also told that when you are expressing the design equation in terms of conversion, what we need to know is the rate law in terms of conversion, because otherwise we cannot correlate the things. So, what we did also, then we went back and we did some simple what may look like simple physical chemistry classes. We derived the rate law. We did, if I remember correctly, one simple problem regarding the derivation of rate laws. So, the rate law will give you the rate as a function of the concentration of different species that are present, and then what you have to do, those concentrations of different species you have to express in terms of conversion, and that is your stoichiometric table. And by combining your rate law with a stoichiometric table, you can get ultimately the expression of rate as a function of conversion. So, then this expression of rate is there in your design equation. So, you replace that expression with the function with the conversion, and then you have your final design equation. So, those things we discussed, and afterwards we also discussed some details regarding CSTR and PFR in terms of if you are aiming for a particular conversion, whether you are going to use more than one CSTR or if you can use only one CSTR. We argued that if you split up, say you are going for 80% conversion, if you use two CSTRs, maybe in the first CSTR you get 40%, and then that you take in the inlet of the second CSTR and you go for 80% finally, then the total volume necessary will be lower. We also discussed this graphically, we also showed this mathematically, and then also we talked about PFR, plugged flow reactor, and we did the same problem, and we told it is the area under the Levenspiel plot that gives you the total volume necessary for the PFR to get a specific conversion, and then you have to solve an integral, and in order to solve that integral you may need to have numerical approach. So, we also discussed things like trapezoidal rule, Simpson's 1/3 rule, Simpson's 3/8 rule, and did some simple problems related to that. In actuality, if I am asking you to solve such problems, certain things will be given. For example, Simpson's 3/8 rule, the formula will be given, or Simpson's 1/3 rule, the formula will be given, because remembering the formula is not the aim of the course, but to be able to apply that to a given problem is what we aim for. And afterwards we moved away little bit from those kind of problems. We talked about CSTR in little bit more detail. We told that not only one steady state, but multiple steady states could be available for a particular reactor condition, I mean for a particular inlet temperature and for a particular heat transfer fluid temperature. And so, not only mole balance, we needed to do also energy balance in order to get a complete picture of the situation, and we also talked about what we call as the ignition temperature and extinction temperature. So, we plotted the rate of heat removal as a function of reactor temperature, or the rate of heat generated as a function of reactor temperature, because many of these radical polymerizations that you do will be exothermic reactions. So, there will be a lot of heat released, so that heat has to be taken away. So, if you are using these energy balance equations, that also gives you an idea about at what rate you have to take away the heat in order to keep the reactor temperature at a particular value, or suppose you want to fix the conversion in this reactor, then what is the temperature at which you have to maintain the reactor in order to get that particular conversion. Those kind of all sorts of variations of problems could be envisaged as far as this thing is concerned. And in detail also we told that the steady state solutions, basically they are nothing but the intersection of your RT versus T curve, that is the rate of heat taken away versus T curve, that curve, and the curve GT versus T, the intersection of these two curves. GT versus T is basically rate of heat generated versus T, and if you have more than one intersection, you have more than one solution, basically then you have more than one steady state, and at each point of intersection the corresponding reactor temperature and corresponding conversion that will define the steady state. So, if you are working at that temperature of the reactor, you get that conversion, and given that you have already fixed your inlet temperature and the temperature of the heat transfer fluid, and we are also assuming here for simplicity that the heat capacity of the reactants and products, they do not change with temperature, so on and so forth. And then we did some simple problems like all the reaction parameters are given, the temperatures are given as far as the inlet temperature and the heat transfer fluid temperature are concerned. Heat transfer characteristics of the reactor are given, heat transfer coefficient, the area of heat transfer, those things are given, and then we ask you to find out the different steady state operating conditions under this situation. And then we finished up with one simple problem of styrene polymerization, where we apply the same concept. So, I hope that this has given you more or less a holistic view. Probably we cannot go into much more detail, and we also did not want to stop at a much simplistic version of the reactor problems. So, I wanted to have a little bit more comprehensive overview. So, I hope that it has given you really a good outlook into the problem, so that it can be used as a basis to build further if you are looking for more detailed courses on, basically this is chemical engineering problems, because this is multidisciplinary field. So, those concepts also are required if you are working in a polymerization plant, so on and so forth, what not. So, what we will do is that we will stop the class today, and from tomorrow onwards we go to the last topic of the course, that is we go into the synthesis of different polymers. So, we start with the synthesis of different commercially important step growth polymers, and what we will mainly do is to concentrate on the structure property relationship. We will not talk about reactors and how we do the reaction in the reactors in a much more intricate detail. No, it will be more like the chemistry options, what kind of temperatures we use, what kind of pressures we use, and you might think these are some details that are difficult to remember, and you will be right. The point is you should remember, if you are doing the reaction at a high temperature, why you are doing at a high temperature. If you have to apply high pressure, why you have to apply high pressure. If you are doing a catalysis, or if you are splitting up the reaction into 2 steps, what are the pros and cons. Those are the aspects that we will actually concentrate on. Not a specific value of pressure, probably you do not need to remember, as long as you know really you are going to go to higher pressure, or maybe at this stage you have to go to higher temperature, probably to distill up some product that has formed, because the reaction is reversible, you want to take the reaction forward. This is one aspect. Second aspect is more we will concentrate on the chemical structure of this, because it is the structure that gives us an idea about the property that we want to develop. Unless we understand the relationship between the structure and property, we cannot really develop the properties. So, those are the directions that the course is going to take in the rest of the week and in the coming week thereafter. So, until the next class then, goodbye and thank you.